Imagine a journey that began over 4 decades ago. A silent odyssey spanning billions of miles, pushing the very boundaries of what humanity thought possible. At this very moment, two intrepid explorers, Voyager 1 and Voyager 2, launched in 1977, continue their relentless hurtle through the cosmic ocean, each traveling at a staggering 30,000 miles per hour. These aren't just machines, they are our farthest ambassadors, the most distant man-made objects ever to leave the embrace of our home planet. On August 25, 2012, Voyager 1 achieved a monumental feat, crossing an invisible frontier into the vast uncharted territory of interstellar space, a place no human creation had ever reached before. This isn't science fiction. It's the living, breathing reality of an ongoing mission that has redefined our place in the universe. We stand on the precipice of understanding the true edges of our solar system. Thanks to these metallic pioneers, still whispering secrets across unimaginable distances, a testament to human ingenuity and our insatiable drive to explore. Their story is one of serendipity, ambition, and a relentless pursuit of knowledge, a journey that began with a unique cosmic opportunity and continues to captivate our imaginations. But the Voyagers carry more than just scientific instruments. They carry a message, a golden, timeless record etched with the sounds and images of Earth, a message in a bottle cast into the cosmic ocean. This isn't merely a testament to human technology, but a profound statement of our existence, a greeting card from humanity to any intelligent life that might one day discover it. While their primary mission was to unveil the mysteries of our outer solar system, this audacious addition transformed them into interstellar storytellers. For decades, these two identical probes have been our eyes and ears, sending back breathtaking images and invaluable data from worlds we could only dream of reaching. They've taught us about the enigmatic heliosheath, the protective bubble around our solar system, and now from beyond, they continue to send signals, pushing the boundaries of our understanding. This dual purpose to explore the known and to greet the unknown encapsulates the daring spirit of the Voyager program, a journey that began with an extraordinary alignment of celestial bodies and a stroke of scientific genius. The very possibility of the Voyager mission hinged on a remarkable cosmic coincidence. In 1965, a brilliant aerospace engineer named Gary Flandreau at NASA's Jet Propulsion Laboratory made a stunning discovery. He noticed that in the late 1970s, the four outer gas giants, Jupiter, Saturn, Uranus, and Neptune, would align in a specific configuration, creating an incredibly rare celestial slingshot opportunity. This grand tour alignment, as it became known, was a once-in-a-lifetime event, a cosmic window that would not open again for another 176 years. Before this, visiting even one outer planet with chemical rockets was a decade-plus endeavor. Visiting all four was unthinkable. But Flandreau's insight, combined with crucial advancements in gravity-assisted orbital trajectories, changed everything. The principle was elegantly simple yet mathematically complex. A spacecraft could use the gravitational pull of a nearby planet to dramatically boost its speed and alter its course, effectively slingshotting it to the next destination. This meant that once a probe reached mighty Jupiter, the solar system's most massive planet, its immense gravity could propel the spacecraft across vast interstellar distances with unprecedented speed, setting the stage for an epic journey of discovery that would redefine our understanding of the outer solar system. Initially, the vision for exploring this rare planetary alignment was even grander, known simply as the Grand Tour. It involved sending a series of sophisticated probes to visit all the outer planets, an ambitious undertaking for the fledgling space age. However, the early 1970s were a period of significant transition for NASA. The Apollo program was concluding, and immense financial resources were being channeled into the development of the Space Shuttle, an ambitious, reusable spacecraft program. Facing mounting budget projections nearing $900 million for the Grand Tour, and with the shuttle's development costs looming, NASA was forced to scale back its interstellar ambitions. The original Grand Tour was canceled, replaced by a more modest, cost-effective mission profile, an extension of the successful Mariner program, initially dubbed the Mariner Jupiter-Saturn mission, or MJS. These new probes would build upon the Mariner platform, incorporating lessons learned from Pioneer 10's groundbreaking Jupiter flyby in 1973. It was this refined, yet still incredibly ambitious, project that ultimately took on the iconic name, Voyager. Despite the initial setbacks and compromises, optimistic NASA engineers secretly harbored the hope that, if successful at Jupiter and Saturn, the probes might just have enough left in them to extend their mission to Uranus and Neptune, resurrecting the spirit of the original Grand Tour vision. When we envision a spacecraft, we often picture sleek aerodynamic lines. But the Voyager probes launched from Earth in 1977 defy this image. Designed for the vacuum of space where aerodynamic friction is non-existent, they are anything but sleek. Weighing 1,592 pounds or 722 kilograms, each Voyager is an identical marvel of engineering built for endurance. The heart of the spacecraft is its main bus, a 10-sided box 5.9 feet across, housing vital electronics, scientific instruments, and a fuel tank for the small rocket thrusters used for orientation. Dominating its profile is the iconic 12-foot high-gain antenna, resembling a giant satellite dish. This crucial component serves as the spacecraft's lifeline, its sole means of receiving commands from Earth and relaying precious data back home across billions of miles. No matter where Voyager travels, this dish remains perpetually pointed towards our distant blue planet. Extending from the main bus are three long booms, carefully positioned to separate sensitive instruments from the power source and other electrical interference. This robust, no-frills design, focused purely on functionality and survivability in the harsh environment of deep space, allowed the Voyagers to embark on a journey far beyond what anyone initially dared to imagine. Powering a spacecraft for a decades-long journey across the solar system and beyond is no small feat, especially without sunlight for solar panels. The Voyagers rely on an ingenious solution: radioisotope thermoelectric generators, or RTGs, positioned on one of the long booms to minimize radiation interference with other instruments. These devices contain pellets of plutonium dioxide. The natural radioactive decay of this material releases heat, which is then converted directly into electricity by thermocouples. Though the power output is modest, it is incredibly long-lasting, providing the necessary energy for the probe's electronics and scientific instruments, a supply expected to endure until at least 2020 and possibly beyond. The other two booms are bristling with a sophisticated suite of instruments designed to scrutinize every aspect of the outer planets and the space between them. These include magnetometers to measure magnetic fields, plasma spectrometers to analyze charged particles, infrared and ultraviolet spectrometers to study atmospheric compositions, and cosmic ray detectors. Perhaps the most captivating, however, are the imaging science system cameras. With a resolution of 800 x 800 pixels, featuring both wide-angle and narrow-field lenses, these cameras returned unprecedented, awe-inspiring photographs of the gas giants and their moons, offering humanity its first truly intimate glimpses of these distant worlds, including the iconic pale blue dot departure shot of Earth and its moon. Given the immense distances and the ever-growing communication lag with Earth, which now stretches to over 14 hours for a one-way signal, the Voyager spacecraft needed to be remarkably autonomous. Engineers anticipated that a craft operating independently for decades, billions of miles away, would inevitably encounter issues. Their solution was groundbreaking: a self-repairing computer system. This sophisticated brain of the Voyager probes was designed with multiple, redundant modules. These modules constantly compare the data they receive and the instructions they process. If one module's output deviates from the others, it is assumed to be faulty, isolated from the system, and immediately replaced by a healthy backup module. This built-in redundancy and diagnostic capability was a revolutionary step for its time, ensuring the mission's continuity even in the face of unforeseen malfunctions. In fact, this system was put to the test shortly after launch when a minor delay in boom deployment was initially misread as a critical malfunction. The self-repairing system successfully identified and corrected the perceived issue, proving its worth and instilling confidence that Voyager could truly brave the cosmic wilds on its own. This foresight in design allowed the Voyagers to continue gathering and transmitting invaluable data long after direct, real-time human intervention became impossible, making them true pioneers in autonomous deep space exploration. The meticulously planned Grand Tour began with a carefully orchestrated sequence of planetary encounters. Voyager 2, though launched first on August 20th, 1977, was soon overtaken by its faster twin, Voyager 1, which launched on September 5th, 1977. This numbering anomaly was a pragmatic choice by NASA, ensuring the public heard from Voyager 1 first when it reached Jupiter. In 1979, both probes spectacularly encountered Jupiter, the solar system's colossal gas giant. Voyager 1 performed a closer flyby, capturing unprecedented details of Jupiter's swirling weather systems, its faint rings, and the bizarre volcanically active moon Io, a discovery that stunned scientists. Voyager 2 followed, taking a more conservative path, gathering complementary data. Both then used Jupiter's immense gravity to slingshot themselves towards Saturn. By 1981, they had reached the ring jewel of our solar system. Voyager 1 made a crucial pass by Saturn's largest moon, Titan, confirming its dense, hazy atmosphere, a decision that irrevocably set its course out of the plane of the planets. Voyager 2 then had its turn, providing breathtaking views of Saturn's intricate ring system and its diverse retinue of moons. These initial encounters were not just engineering triumphs, they were scientific gold mines, immediately rewriting textbooks and igniting public imagination with vibrant, high-resolution images of worlds previously known only as fuzzy telescopic blurs. While Voyager 1's trajectory, optimized for the Titan encounter, sent it soaring out of the ecliptic and eventually out of the solar system, Voyager 2 had a different, even more daring path. If it could survive its Saturn encounter, it was destined for a long-shot extension, a journey to the distant ice giants Uranus and Neptune. This was a gamble, considering the spacecraft were already years past their initial mission objectives and operating far beyond their design lifespan. Yet, miraculously, Voyager 2 continued to function flawlessly. In 1986, after a nearly 5-year journey from Saturn, Voyager 2 arrived at Uranus, revealing a world unlike any other. It discovered a planet tilted almost on its side, with a uniquely skewed magnetic field and a family of previously unseen moons and faint rings. But the grand finale was still to come. After another 3-year journey boosted by Uranus's gravity, Voyager 2 reached Neptune in 1989. This encounter, occurring more than a decade after launch, unveiled a dynamic blue world with surprising winds, a great dark spot comparable to Jupiter's famous storm, and several new moons, including Triton with its active geysers. Against all odds, Voyager 2 had completed the Grand Tour, a monumental achievement that pushed the boundaries of exploration and transformed our understanding of the outer solar system from mere speculation to detailed observation, proving that the spirit of exploration knows no bounds. The sheer volume of scientific data returned by the Voyagers is staggering. By 1989, it was estimated to be enough to fill 6,000 editions of the Encyclopedia Britannica. But it wasn't just quantity, it was the quality and transformative nature of the discoveries. From Jupiter, we gained our first detailed understanding of its complex weather patterns, its powerful magnetic field, and the stunning revelation of active volcanism on its moon Io, a level of geological activity unheard of for a moon. Saturn's enigmatic rings were resolved into thousands of individual ringlets, and the true atmospheric density of its largest moon, Titan, was measured, paving the way for future missions. Uranus revealed its incredibly peculiar magnetic field, wildly askew from its rotational axis, challenging existing theories. And Neptune, the farthest giant, surprised us with supersonic winds and a gigantic Earth-sized storm, the Great Dark Spot. Beyond the individual discoveries, the Voyagers provided the first comprehensive, close-up portraits of these distant worlds and their diverse moons. These brilliant images and the wealth of data fundamentally reshaped science textbooks, informed public perception of our solar system, and laid an indispensable foundation for every unmanned space mission that has followed, inspiring generations to look up and wonder. Even after completing their primary mission, the Voyagers continued their epic journey, venturing into the truly unknown. In 2007, both spacecraft entered the heliosheath, the outermost layer of the solar system, a vast region where the solar wind, streaming from our sun, battles with the interstellar magnetic fields. This dynamic boundary marks the true edge of our star's influence, creating a shockwave and a turbulent environment. The Voyagers, serving as our probes into this frontier, traversed this shockwave and began sending back crucial data, providing astronomers with their first direct measurements of the heliosheath's shape, location, and conditions. But the greatest triumph was yet to come. On August 25, 2012, after 35 years of travel, Voyager 1 officially crossed the heliopause, the ultimate boundary where the sun's influence ends and true interstellar space begins. This historic moment, confirmed by a dramatic shift in particle data, made Voyager 1 the first man-made object to venture into the vast cosmic sea between stars. Though some instruments have inevitably ceased functioning after decades of exposure to harsh radiation, both Voyagers continue to transmit vital information, sending back insights from beyond our solar system, teaching us about the interstellar medium, and reminding us that the journey of discovery never truly ends. Beyond their scientific instruments, perhaps the most profound payload carried by each Voyager is the Golden Record. This 12-inch, gold-plated copper phonograph record is a deliberate message to any intelligent extraterrestrial life that might one day intercept the spacecraft. Curated by a team led by Carl Sagan, the record is a time capsule, a carefully chosen symphony of Earth's sounds and sights. It contains 115 images encoded in analog, depicting mathematical definitions, our solar system's location, human anatomy, diverse cultures, and natural landscapes. It also features a vast array of natural sounds, crashing waves, wind, thunder, birdsong, and animal calls, alongside a selection of music from various cultures and eras, including pieces by Bach, Beethoven, and Chuck Berry. A spoken greeting in 55 different human languages, and a message from then U.S. President Jimmy Carter complete this cosmic calling card. The probability of an alien civilization ever finding, let alone deciphering, these records is infinitesimally small, yet their existence is a testament to humanity's innate curiosity, our desire to connect, and our profound hope that we are not alone in the universe. It's a grand, poetic gesture, a symbol of humanity's aspiration to reach out beyond the confines of our world, an enduring whisper into the cosmic void. The Voyager program, initially conceived as a relatively modest extension of earlier missions, transcended all expectations to become one of humanity's most successful and enduring endeavors. Its legacy stretches far beyond the scientific data it returned, which fundamentally rewrote our understanding of the outer solar system. Technologically, the Voyagers pioneered deep space communication techniques, validated the concept of long-duration autonomous spacecraft operations, and pushed the boundaries of self-repairing systems. The experience gained from designing, launching, and operating these probes laid an indispensable foundation for virtually every unmanned space mission that followed, shaping the architecture of modern space exploration. But perhaps its most profound impact is inspirational. The stunning images of Jupiter's Great Red Spot, Saturn's majestic rings, and Neptune's vibrant blue hues ignited a sense of wonder in millions around the globe. They transformed distant, abstract points of light into tangible, dynamic worlds, fueling public enthusiasm for future space exploration and inspiring countless individuals to pursue careers in science, engineering, and astronomy. The Voyagers aren't just scientific instruments. They are symbols of human ingenuity, resilience, and our unyielding quest to understand the universe we inhabit, a testament to what we can achieve when we dare to dream big and look far beyond our immediate horizons. After more than 45 years in space, the Voyagers are true cosmic marathons, yet even their incredible journey must eventually draw to a close. The RTGs, which have faithfully powered them for decades, are slowly, inexorably losing their output. While some instruments have already been shut down to conserve power, and others have simply ceased to function, the remaining active instruments continue to send back invaluable data from the interstellar medium. The communication window with Earth, already challenging due to the vast distances, will become even more precarious as power levels dwindle. Eventually, perhaps in the late 2020s, the power will deplete completely and the Voyagers will fall silent, their last whispers fading into the cosmic background noise. But their mission won't truly end. Long after they stop transmitting, these resilient spacecraft will continue their silent, eternal journey through the galaxy, carrying their golden records and their incredible story into the unimaginably distant future. They will become relics, testament to a small blue planet that once reached out, touched the stars, and sent its children on an impossible quest. The Voyagers are not just fading echoes, they are eternal pioneers, continuing their journey as silent monuments to human curiosity, drifting through the Milky Way for eons, perhaps forever.